One time, our school had a no book, no backpack day. One single day where you needn't worry about academics. A whole day dedicated to having fun. All was going well, and we were all having fun. But out of the blue, our maths teacher declared that we were going to play bingo. But it wasn't the everyday normal kind of bingo. It was. This is how a game of classic bingo is played. Each person has a sheet which looks something like this. There are 25 squares, of which 24 of them have numbers, and the center one is free. The first column can be filled with numbers from 1 to 15. The second column can be filled with numbers from 16 to 30, and so on. A random letter number pair is called out, and the players who have that particular pair strike it out. This process continues till one of the players has struck out either an entire row, an entire column, or a diagonal. There is no limit to how many letter number pairs are called out. The game only stops when there is a winner. And this is how math bingo is played. Each person is given a sheet which looks something like this. A square grid with 25 numbers filled randomly from 1 to 50. No free square. But instead of numbers, our class watched in horror as our teacher began to call out 25 math problems. We had to solve these math problems, take their answers, and check if we had that number. If we did, we had to strike them out. Moreover, instead of getting just one row or column or diagonal, we had to get 5 for it to be considered bingo. And the game stops after all the 25 numbers are solved, irrespective of whether or not there's a winner. Obviously, after just 25 numbers, it would just be too insanely improbable. A winner within 25 turns. What were the odds? This enraged me, who then naively proceeded to embark on a perilous journey of calculating exactly that. The odds of winning this bewitched game. To my utter surprise, this terrible sin of a game had made 2 other people in my class question their entire life and existence. We spent the next couple of hours together, unwinding into insanity as we slowly discovered the sheer scale of the complexity before us. As simple 12th standard students, equipped with nothing but NCRT and R.D. Sharma, we had little to no idea on how to solve this using theory. There were simply way too many cases to consider. We did, however, find one thing: the total number of bingo sheets possible, which turned out to be this. Okay, let's look at the problem statement. What is the probability of a random sheet to display bingo within 25 turns? The average probability enjoyer will let you know that this is equal to the number of sheets which give bingo divided by the total number of sheets. Well, we have this part. What about this? I guess it should be pretty easy to calculate. That day, the 3 of us realized just how unintelligent we were and accepted defeat. But a seed was planted that day. A seed which slowly grew into a troublesome plant which rooted itself in my brain, stopping me from thinking about anything except that for days. No matter how much I tried, I couldn't come up with a solution. The motivation died down, and for months, the question would lay dormant with little progress. Fast forward to now. I finished school. I started learning Unreal Engine to make cool games and become a zillionaire. And by chance, I glanced at the working of the bingo problem and realized that the calculations needn't be done by me. I could make my computer do it. With this newfound realization, I had just the perfect tool I needed. After creating a quick prototype with blueprints, I had my proof of concept. It worked, but at what cost? It ran slower than me, and believe me when I say I cannot run. This was not just because I am bad at programming and my code was severely unoptimized, but also because of the limitations of the platform itself. I was using something made to write high-level game logic to run a computationally intensive math problem. So it was time to switch out to the big guns. No, not that. The fastest available programming language. You may be screaming internally, but C++ is considered to be one of the most difficult languages to master. Why would you choose something so difficult? To you I say, master is the key word. Mastery in C++ requires decades of experience and tons of projects. But turns out, writing noob math algorithm code isn't too difficult. After suffering for like 5 hours and completely rewriting my code 3 times, I finally got everything to work. Here's the code. If you really want to run it yourself or bully me for writing brain dead code, I have linked my GitHub page in the description. Alright, now for the big reveal. After running the program for 100 million sheets, the probability of a random sheet winning at a game of bingo within 25 moves is a total of 1603 sheets out of 100 million sheets had hit bingo. That's all? That's like 1 in every 62,500. In comparison, in a standard game of bingo, if 100 players are playing and each person has 1 sheet, the probability of your sheet winning is 0.01, 625 times more likely. Then how could someone possibly be that astronomically lucky? The odds are simply too small for a random sheet to give bingo. There must be a simple solution to this dilemma. In reality, the questions were probably set with numbers from the winning sheet in hand to make sure that there was always a winner, and then the sheets were probably randomly shuffled and distributed. Was this a fair skill-based game, no exploits whatsoever? Probably not. But was it a fun break from the monotonous everyday schedule? No. It caused stress, anguish, and months of maths. But finally, it's done. I can now rest well knowing the exact odds of winning this twisted version of bingo. But if you look closely at the code, our value isn't exactly exact. There are 2 ways to calculate the probability of an event. There is the theoretical approach and then there is the experimental approach. Theoretical probability is where we say the coin has 2 sides, a head and a tail, and they are both equally likely. So the probability of getting heads is exactly 0.5. This is the elegant mathematical approach. This is the pinnacle of accuracy. And then there is the experimental probability, kind of like a dirty shortcut method. Here, we simply throw the coin a million times and observe the number of times it shows head. If it shows head 503,125 times out of a million, the probability of getting heads can be approximated to this, which is pretty close to the actual 0.5. But it'll always be a crude approximation. With this method, however, higher the sample count, the closer your value is to the actual thing. So I ran my program again, but this time for a billion unique sheets to figure out how many of them gave bingo. And pretty much the exact same thing. This took my computer 9.5 hours to figure it out. 9.5 hours! So if any 300 IQ gigabrain person watching this wants to optimize my code to run it faster, please give me a number! Please. Oh, also, I ran it to find the probability at different number of turns, so here's a cool graph, I guess. Pause. If you made it till this far into the video, 1. Thank you. 2. It's time for the code. Again, let's consider the problem statement. What is the probability of a random sheet to display bingo within 25 turns? There are this many possible bingo sheets, but you and I both know there is no way we can simulate that many sheets at the speed I am doing it right now. That would take something like this many years, way more than the age of the universe. So we gotta settle for a much smaller sample size, in our case, a billion. In my implementation of the code, I decided to use arrays instead of matrices. Matrices are generally used to represent 2-dimensional structures, like a grid of numbers. But in our case, we can get away with a simple 1-dimensional array. The first row of the grid is represented by the first 5 indices of the array. The next 5 indices represent the second row, and the next 5 represent the third, and so on. This way we can model our two-dimensional grid as a one-dimensional array, making it easier and faster to work with. For calling out 25 random numbers, I initialize this array with numbers 1 to 50 and shuffle it randomly. Then I take the first 25 numbers of this array to get a list of 25 random numbers in the required range. I use the same method to generate the bingo sheets as well, but that generation has to be done inside the main loop body, as each sheet needs to be random and unique. Next we gotta compare the numbers called out and the generated bingo sheet to see how many lines were struck out in that specific sheet. However, here I decided to generate an intermediate step. I created yet another array, but this time the array didn't contain numbers. It represented which squares had been struck out. This may seem like an extra step, but hear me out. Without this step, for each line we check, we have to search through the entire array of numbers 5 times. 5 times for each line, and there are 12 lines. That adds up to checking the array 60 times. But by generating a hit sheet, we only check the array 25 times. Running through an entire array and checking if a specific number is there is a computationally intensive step. So by reducing the number of times we do that, we can get a pretty decent speed. In the next step, we simply run this line detection thing on the hit sheet we generated and figure out which lines are completely struck out. As a final step to see if we have bingo, we see if we have 5 or more lines struck out. If we did, we got bingo. And we repeat this process a billion times. Side note number 2. You may have noticed that a bunch of code has been commented out. That is because they were written as temporary debugging tools to make sure everything was working. However, I was informed by the internet that logging information onto the console or onto files on the computer was a pretty time-intensive task. So I had to remove it. But I didn't want to delete my precious. So I just commented them out. But what I didn't realize was that with no logging, we get no logging. Meaning if the program gets terminated before it completes, we have absolutely no usable data whatsoever. So hours of compute would amount to 0 data if something like a power cut were to shut down my computer. But what are the chances of a power cut happening? So I re-implemented the logging to just log out the data related to the sheets, which gave bingo.
A small price to pay
For protection against power cuts. With all that being said, this is still not the mathematically accurate way of doing things. A proper theoretical explanation must be there for this number. So I invite you, the mathematician in you, to try and think about the theoretical explanation for this problem. And let me know if you figured it out. And see you in my next rabbit hole of a random thing, I guess.